Alright, welcome back. This video will be about scientific notation. So scientific notation is used by the field of science to write extremely large numbers, long numbers, or extremely tiny numbers in a shorter way. So scientists have come up with a way to write these numbers in a shorter way. So let's say we have 483 billion and we want to write this in a shorter way. What we have to do is take our decimal, which is not anywhere here to be seen, so therefore it has to be at the end, and you have to move it until it goes right after the first non-zero digit. The first non-zero digit is not these values. The first one will always be the one all the way to the left. So the first non-zero digit that we see on the left side would be the 4. You want this decimal to go right after the first non-zero digit. And so the answer will come out to be 4 and 83/100ths. Now the zeros are not worth any values here, but we do have to count how many spaces we moved to go from here all the way to there. So count spaces: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we moved 11 times. Now, for this number is not worth 483 billion. For it to be, again, worth the same exact amount as this, and we want it to be equal to this. So for it to be equal, we have to multiply it by 10. Now, multiplying it by 10 means taking your decimal and moving it over and making it larger one spot for every time you multiply it by 10. We moved our decimal 11 times. And therefore, for this to go back from there to the original spot, you have to go back 11 times. You have to multiply by 10 11 times. So the amount of spaces you moved is your exponent, and you're always multiplying it by 10. The first digit has to be non-zero digit. So this has to be non-zero, which is okay. Everything else. Now, if you were to, just to check on this, here's a little proof. Let's change it. It's 4 and 83/100ths. And if I'm multiplying it by 10 11 times, here's what happens. Times 10 times 10, that's twice. So I need to do it 9 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Drop, fill in the blank space with zeros. Okay, erase the old decimal. And you don't need these loops anymore. Let's just see if we have the same number, 483 billion. Let's see, so comma here, comma here, comma here. We have 483 billion again. And so this is a quick way to check if you got the right answer. Counting also works. So this amount is worth the same thing as 483 billion. They have to be equivalent to each other. Okay, so we have 81 10/1000ths, which is a very tiny number. In order not to have these zeros here and to make this a shorter way to write this value, we're going to take that decimal and move it over until it goes after the first non-zero digit. So these are all zeros, we can't put them here, but the first non-zero digit we see is the 8. So the answer comes out to be 8 and 1/10 multiplied by 10. Now, this is a small value. When thinking about small values, you have to think of it also as negative values in this case when you're doing scientific notation. So the exponent is going to be negative because we're talking about a tiny decimal. We're going to multiply it by 10, but kind of backwards now. How many times? We have to see how many times we moved it first. So this is going to be once, twice, 3 times, 4, 5, 6, 7, 8, 9. So this is to the negative 9th power. Now, it's the same thing as having 8.1 multiplying by 10 to the negative 9th power is the same thing as having it 1 over 10 to the 9th power. So when you multiply these values, you're going to get 8.1 divided by 10 to the 9th. When you divide this, you're going to get a very tiny decimal. And so dividing a number by 10, when you're thinking about dividing, if you take 8.1 and you're dividing it by 10 9 times, here's what you have to do. The shortcut to divide any number by 10 is move the decimal over by 1 space. In this case, you're dividing by 10 9 times, so you go 1, 2, 3, 4, 5, 6, 7, 8, 9, drop it off, fill in the blank spaces with zeros, erase the old decimal, and you're left back with where you started, a very tiny decimal. Now, we don't need this decimal right now, but here's the proof of why this happens. So, to check whether this works, multiplying by 10 to the negative 9th power is the same thing as dividing it by 10. Multiplying by 10 to any negative power, whatever it is the same as dividing the number by 10. The exponent tells you how many times you have to divide. So let's solve a couple problems to change them into scientific notation. So we have large values. These are not decimals, so our exponent is not going to be negative. It's going to be a positive exponent. The decimal in this case is at the end, so you have to move it until it goes after the first non-zero digit, which is right after the 3. And in this one, the decimal is in the wrong spot. You have to move it until it goes after the first non-zero digit, which is right after the 4. So in the first problem, the answer is 3 85/100 times 10. Count how many spaces we had to move. 1, 2, 3, 4, 5. So the exponent is 5th power. Second one, it's 4 67/100 multiplied by 10. We had to move the exponent once, twice, so it's the 2nd power. Okay, 2 more simple examples. So we have to take that decimal and move it after the first non-zero digit. Same thing in this case, move it after the first non-zero digit. Both of these values were decimals. Therefore, your exponent is going to be a negative exponent. When you're multiplying it by 10, it's going to be a negative exponent. So we count how many spaces we had to move. Once, twice, 3 times, 4 times. So it's the negative 4th power, and it's 8.6. This one is 4.8. We had to move it once, twice, 3 times. Remember, every time you have a tiny decimal, the exponent becomes negative when you want to change it to scientific notation. Here are 2 more examples that look like they might be scientific notation, but they are actually not the correct scientific notation. In the first one, you have a double-digit number followed by a decimal. It should be only a single-digit number followed by a decimal. In the second one, you have a 0 in the first place, and you can't have a 0. So that decimal actually has to go right after the 8s. So we're going to fix both of these for them to be in the correct scientific notation. The first one, I have to take my decimal and move it over 1 space. So the answer comes out to be 3.896 times 10. Now, if I wanted to go back to the original spot where it used to be, I would have to multiply it by 10 one more time to go back to the right 1 spot. So instead of having it 4 places, it changes to 5. If you wanted to write this out the long way, this first one was 38.96. If you multiply it by 10 to the 4th, it's 4 places over. 1, 2, 3, 4. Drop it, and you have this answer. And if you check if this is the same, 3.896 multiplied by 10 to the 5th power, so you move it over 5 spaces, 1, 2, 3, 4, 5, 0, 0, you have exactly the same number, and you want it to be the same exact value. You just want it to be written correctly, and this is the correct way to write scientific notation. First digit is non-zero digit, so anything from 1 to 9 would make sense, followed by a decimal. In this one, the next problem, we're going to move this over to the right one space, so it becomes 8 and 60/100ths multiplied by 10. Now, I have to go backwards one space. Backwards is negative space to the left for it to be the original value. So instead of having 10 to the third, it has to be 10 to the second power. You can prove it by taking the original, multiplying by 10 3 times. So go 1, 2, 3. So the real value 861. Second one, 8.61 multiplied by 10 twice. So you go over 1, 2, and you also get 861. But the second value is the correct scientific notation. Okay, 2 more problems. They're giving you, let's say a question gives you scientific notation and you want to change it back to standard form. Standard is the regular way you see a number. So in the first one, they're multiplying by 10 to the negative 3. Remember that 10 to the negative 3 is the same thing as 1 over 10 to the third. So you are really taking this number and dividing it by 10 3 times. When you're dividing this number by 10 3 times, every time you divide by 10 once, you move it over, make it smaller by one place. So you go 1, 2, 3, extra 2 zeros, decimal, and 0. So this number becomes 0.00832. 832 10,000ths. And in the next one, we are just multiplying it by 10. We're doing it 6 times. So 4.65, take your decimal, move it over 6 times to the right, because you're multiplying by 10 now. You're not dividing like in the last one. You're multiplying by 10 6 times. 1, 2, 3, 4, 5, 6. Drop. 0, 0, 0, 0. So 4, 6, 5. How many zeros? 1, 2, 3, 4. Comma here. So we have 4,650,000. Okay, if you ever come up with a question like this, when they're asking you to take scientific notation value and multiply it by a standard form, you probably want to change this first into standard form to make it not as complex for you to understand. So take this original value as 5 and 8/10. You're dividing by 10 6 times because this is a negative power, so you're going to go divide once, twice, 3 times, 4 times, 5 times, 6 times. Decimals now here. These are zeros. Okay, and then we are taking this value, 1, 2, 3, 4, 5. That's the new value. That's the standard form of that version. And we're going to multiply it by 1,000. Okay, to multiply any number by 1,000, it's the same thing as multiplying it by 10 to the third power. So you're going to take this decimal and move it over once, twice, 3 times. So this becomes 0.0058. Now, if you understand the rules of exponents, you could have also done it up here. If this is the same thing as 10 to the third power, you take your exponents. If you have the same base, these are both 10s, and you add the exponents. It's the same thing as 5.8 times 10. Negative 6 and positive 3 gives you negative 3. So if we take 5.8 and drop it 3 places, 1, 2, 3, you do get the same exact answer as before. There we go. So this is the same as that. You can apply the power of exponents, or you could change it first. There's a couple different ways you can do this. All right, good luck.